Hello, this is Mr. Huebner. In this video we're going to be going over the different types of bonds. There are two main bonds. As we talked about earlier, there's ionic and covalent. And if we talk about covalent, there's two subcategories. There's polar covalent and nonpolar covalent. And then we have metallic bonds. Alright, so this first one, ionic bonds, are essentially the stealing of electrons. And I say stealing because that's personification, so it's technically the transfer of electrons from one atom to another that creates two charges. And we said the electronegativity difference, remember, is 1.6 or more, 0.6 or more. Between the two different atoms that make up that ionic compound. If they form a 1.6 electronegativity difference or more, it is ionic. So let's just do a quick little example of ionic, what it means to transfer electrons. We've got sodium and we have chlorine. And chlorine has 7 outer electrons. Let me just throw a little picture up here. We have column 1, these have 1. These have 2 electrons. We're talking about valence, outer electrons. These have 3, carbon group has 4, nitrogen 5, 6, 7, and the noble gases have 8. So we're talking about chlorine. These have 7 outer electrons, and sodium has 1. Rule of thumb is the one that has more electrons typically is more electronegative. If you don't remember, you can check this electronegativity table. We got chlorine is 3, and sodium is, where is sodium? Oh, there it is, 0.9. So 3 minus 0.9 is 2.1. That's definitely ionic. And since 3 is a higher number, this is more electronegative, so chlorine is going to be stealing or receiving those electrons in the transfer. Alright, so switching back to here, we got a Lewis dot structure, which we're going to talk about in another video. But it has 1, 2, 3, 4, 5, 6, 7, and those dots represent outer electrons. And sodium has 1. Unfortunately, I have a pen. It would be best for you to use a pencil because I want to show that this electron gets transferred over to the chlorine. So I'm going to rewrite this since I'm in pen. And if sodium loses an electron, we know it has a positive charge. And if chlorine gains an electron, it gained that electron, we know it has a negative charge. And that would be the Lewis dot structure of an ionic compound that's showing the transfer of electrons from one atom to another, creating an electrostatic attraction. It's a very, very strong bond. So let's write some more notes. Very strong, high melting point. Because of that strength, it's got a high boiling point also. Forms a crystal lattice. Alright, I just popped up a picture of what a crystal lattice looks like. What we got is sodium and chlorine, and they are interspersed in a nice consistent pattern. So what we're showing right here is sodium is surrounded by a chlorine, a chlorine, a chlorine, a chlorine, a chlorine. Essentially, if you think of it as a cube, sodium is a cube. Cube has 6 sides, so it has 6 chlorines, 1 chlorine connected to it on each side. And likewise, each chlorine has a sodium next to it on each of its 6 sides. And that is what we call a crystal lattice. It's a very strong bond. Has a lot of lattice enthalpy energy, we call it. The energy in a bond creates a high melting point, high boiling point, very brittle compound. Did we write brittle yet? No. Brittle. Alright, moving down. We got dot diagram. I already showed you the dot diagram in this. or sodium chloride. Characteristics, I think that's where I was supposed to write all of this. This is kind of a big box for a little definition there, but maybe you write big, so thinking for everybody. Moving on, let's do covalent bonds. There's two types. There's polar covalent and there's nonpolar covalent. So essentially, for both covalent, whether it's polar or nonpolar, it's the sharing of electrons because the electronegativity difference isn't as great. It's basically 0 to 1.6, less than 1.6 is the electronegativity difference for covalent in general compounds. If we're talking about polar, it's going to be 0.4 to 1.6 is the electronegativity difference. So the difference isn't as high, and in nonpolar it's even smaller. It's 0 to 0.4 is the electronegativity difference. So they're virtually the same almost, like nitrogen, N2. They have the same electronegativity value, therefore their difference is 0. So they have to share their electrons equally, essentially. Alright, getting onto the definitions. So polar covalent is unequal sharing of electrons. It's kind of like big brother, little brother. Big brother is stronger, more electronegative. Therefore, it's going to be able to play with the toys more of the time, because when the parents aren't looking, the big brother kind of gets to do what he wants because he's bigger. Going to nonpolar covalent, this one is the opposite. It's equal sharing of electrons. This would be if you had twins. They both have equal strength, so they're going to duke it out and eventually be playing with the toys around the same amount of time. Equal sharing of electrons is nonpolar. It has to do with that difference in electronegativity is relatively minimal, small. Alright, characteristics. This is going to be low melting point, low boiling point, does not conduct electricity, whereas ionic compounds do conduct electricity when they are dissolved in water or they are in their liquid molten state. Whereas covalent substances, they're not going to conduct at all. Not conductive of an electric current. Whereas ionic compounds are typically going to be solids, covalents are going to be liquids and gases. At room temperature, at least. I mean, they can still be solids if you get them cold enough. Alright, I want to go over the Lewis dot diagrams. We'll do it on this sheet right here. Why don't we pick a fun little covalent compound like water, H2O. So what we got to do for this, we have multiple atoms here. So it's more than two. We got to pick the one that's in least supply. Typically the one that's more electronegative is going to be the central atom. Also the one, or you could think the one that has the least amount of bonding sites. So if you have like sodium has one bonding site. If you have something like magnesium, it's two bonding sites. Boron has 1, 2, 3. Carbon has 1, 2, 3, 4, whereas nitrogen has 1, 2, 3, 4, 5 bonding sites. Which one has more bonding sites? Carbon or nitrogen? 1, 2, 3. 1, 2, 3, 4. Anytime you have a single dot or electron by itself, that is a bonding site. If you have two electrons next to each other, that's called a lone pair. It's a non-bonding pair, not involved in bonding. So in this case, carbon would have 4 bonding sites versus nitrogen having 3. Carbon is going to be the center atom. So looking at hydrogen, hydrogen has 1 valence electron, oxygen has 1, 2, 3, 4, 5, 6. How do I know this? Alright, let's go to a periodic table and show it. If you're in column 1, you have 1 outer electron. Column 2 has 2, 3, 4, 5, 6, 7, 8. That's how I know hydrogen has 1 valence electron and oxygen has 1, 2, 3, 4, 5, 6 valence electrons. And how I write the valence electrons is a single dot, single dot, single dot, single dot. Once I have more than 4, then I can start pairing them up. So 5, 6, and that's why these are paired up. Alright, so I already have oxygen, I've got hydrogen. I'm going to put another hydrogen over here which has 1 valence electron. I'm doing that just to make a pretty picture because I got a single dot, they're going to come together, single dot, they're going to come together. Now that's a very simple molecule. It's a simple way of doing a Lewis dot structure. In a later video I'll show you how to do a process of making Lewis dot structures so that it works for all situations, even the weird exceptions to the octet rule. So there we go. This is different than how we were doing ionic compounds. Ionic compounds is showing a transfer of electrons creating an electrostatic attraction caused by charges due to the high degree of electronegativity difference. It's a little bit different with covalent. Covalent, we said, was sharing electrons. So we got to show sharing by a line. A line shows sharing. So we got this electron from hydrogen and that electron from oxygen, both being shared so that hydrogen has 2 outer electrons. Now this is weird. Typically they want 8. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8, and it satisfies its octet rule. Typically all elements want to have 8, but there are exceptions. Hydrogen is one of those exceptions. It has to do with the electron configuration. Remember, hydrogen is 1s2, but then if we move on, it's 2s2 and then 2p6 and so on. The first energy level just has 2 electrons possibility. A max of 2 electrons could be in the first energy level. So hydrogen and helium being the first 2 elements, they want, actually they only have the capacity to have 2 outer electrons. So they don't want 3, they don't want to have 8, they want 2. It has to do with the electron configuration. Whereas the next energy level has 2s2, 2p6, has 6, 7, 8. 8 outer electrons, and that's typically the magic number unless, of course, you're hydrogen or helium or one of the few other exceptions. For this class, we're going to be focusing on the standard, the things that are common, not the exceptions. Alright, so that's a Lewis dot structure for a covalent compound. Alright, and the last thing we want to go over is metallic bonds, and that's right here. Alright, metallic bonds is essentially positive nuclei surrounded by a sea of free-flowing electrons. Positive nuclei surrounded by a sea of free-flowing electrons. We'll draw a picture before we add more details, but let's say we're talking about iron. Iron's a common metal. Iron, we got positive nuclei, and we've got a sea of negative electrons that are free-floating. This is how you draw a metallic bond. A little bit different than Lewis dot structures. This is what causes metals to be very malleable and ductile. Alright, so malleable means can be pounded into sheets. Ductile means can be spun into wires. Alright, so this is unlike ionic compounds. Ionic compounds are soluble in water. Metallic bonds are not. So insoluble in water. High melting points. Very conductive of electric current. Alright, so those are some characteristics of metallic bonds. That's ionic, covalent, and metallic. Remember, covalent has 2 types, polar and nonpolar. Unequal sharing versus equal sharing electrons. Ionic is a total transfer of electrons. Alright, that's the video. I hope you enjoyed. Have a great rest of your day.